Okay. So now, removing elements from a binary heap. So as we have now looked from to these underlying information with the underlying things with binary heap. Now the removing elements are a bit advanced, are a bit more advanced than, for example, adding or turning min priority queue into a max priority queue. Okay, now let's look at the removing elements from a binary heap. Now we have on the left a list of instructions, a pull and a remove instructions. So in general, with heaps, we want to remove the root value because the node at the top of the this heap, because it's the node of interest. So because in heaps it has the highest priority, so it is either the smallest element or the largest element, the smallest value or the largest value. So when we remove something, we call it just removing. But when we remove the root node, we call this pulling. So a special thing, the special thing about removing from the root node is that we don't need to search for the index node. We don't need to find its index, its position in the array, because in the implementations based on the arrays, but not based on the unordered list, but on the arrays, the position or the index of the root node is always 0. So that is the first node. That is the very first node in the array. Okay, now let's look at the first instruction, that is to pull. So we are removing the root node, and the node in red is the node we want to remove. In this case, that is the root node, because we're pulling, we're removing the root. And in purple, we are highlighting in purple the last node in the priority queue, in the binary heap, the last node. So in the array implementation, for example in Python, that is -1. That is an element with the index of -1 or -1. So that is the very last, the rightmost element in the in the binary heap, and that is the last element in the array. So that is in purple. That is because we know its position, we know its index, and so we are swapping them. We're swapping the 10 node, that is the last node, and the 1 node. So now 1 at the last position, at the position of the last node. So here now we want to remove this 1, so we're just removing it. And now we have the violation of the heap invariant, as 10 is as 10 is greater than 5, and 10 is a parent node of 5. So that means we want to bubble it down or sync it. So and when we have the situation when there are nodes that are both less than 10 or less than our node, but they're both less, but one of them is greater than other, we're going to swap it with the node that is less than. So we want to swap it with the smallest, if we can refer to it, node. So in this case, that is 1. So 5 is greater than 1, so we're swapping it with 1. And also here, if both nodes are less than 10, if both nodes are less than the node we want to swap with them, to bubble it down, we want to select the left node, in case of a tie like this. So here we have two nodes, and that is why we swap it with the left one, and we again swap it with the lowest, not lowest, but the root with a smaller value, and that is 2. So we're swapping it, and now the root of the heap invariant is satisfied. So this means that we successfully polled the root, or removed the the root element, and so that is for polling, where it's just removing the root and then sinking it or bubbling down the node that was the last position after we swapped it in. But however, we do not always sink or bubble down the node, the last node, especially when we remove some arbitrary nodes. So now let's remove 12, and we'll see that we're going to bubble it up. But however, first we need to find 12 because we don't know where it is. Where is it in the heap? We don't know its index, or rather the computer doesn't know where it is. So first we find 12, and we need to do a linear scan across all the nodes until we find 12. So we're starting from the root node. So 1 is not 12, and we're going to the next layer. 5, 2 also are not 12. So the values of this nodes are not equal to 12, and we're continuing to process every element in the priority queue in the binary heap before we meet 12. So here it is. We have found it, and we're highlighting it in red, and in purple we are highlighted the node, the last node in the array, in the mean heap. So we're swapping them with these two values, and next we are removing 12. So after we swap them, we can see that we're in violating of the heap property because of 3 is less than 8. So in this case, we want to bubble it up. So we'll swap 2, 3, and 8, and then we swap 5 and 8 because 5 is also greater than 3, but 3 is greater than 1, and we don't swap it, and so we're not violating the heap invariant, and so this node is removed. So 12 is removed successfully, and now we want to remove 3. For example, first we want to find it. So as we found it, we swap it with the root node, swap it with the last node in the heap, the binary heap, and remove it as before. So now we bubble it down, we sync it. So now, okay, so we need to bubble it up. Oh no, we need to bubble it down because we already satisfy the heap invariant from above, since 15 is greater than 1 than the root node here. So we bubble it down. So we bubble this down, and we're syncing it. In other words, we are syncing it, And now 15, So also important that we are swapping it with 5 because 5 is less than 6, and so we're swapping it with 5. And next, 8 is greater. 8 is less than 13, and that is why we're swapping it with the 8, not with 13, because we want to swap it with the element that is less, which value is smaller. And now we are satisfying the root invariant, and we can also try to poll. We remove the root node, and so we're swapping 1 with 10 with the last node, node at the last position, and removing 1, and then we're swapping it with 2, since 2 is less than 5. And now, again, both left and right children have equal value. So which do we need to pick? Which we will pick? Yeah, we want to pick, select the left child. In this case, in the case of a tie. So here, we're swapping 2 and 10, and now the heap invariant is satisfied. So we want to remove 6, where first we want to find it. 5, 2 are not 6, 8 is again not 6, and as we found 6, we swap it with the last node, that is 7. So we first have to remove every node on the last level on the layer, on the last level before moving to the next level. So now we are going to swap it with these 4 values on this branch, and not going to any higher before we have these 4 root nodes. And so we're swapping it with 7, removing it. And do we need to bubble it up or bubble down? So 5 is less than 7, and 11 is greater than 7. That means the heap invariant is already satisfied, and we don't need to swap it neither with 5. We don't need to neither bubble it up or bubble it down, because it is already satisfied. And now we see that from this polling and removing, we can conclude that the following: that polling takes logarithmic time, since we're removing the root node and we already know the index of the root node, and we know where to find it and with which we want to swap it, and so this logarithmic time creates only that we need to swap it sometime, yeah. But removing from a random node or from a arbitrary node takes up to linear time, or time of O of n, since we have to find the node we want to remove before we remove it. So we have to we need to do a binary, not binary but linear search before we would try to remove it. However, some programmers are dissatisfied with this linear removal, so there are some other ways that can be better to improve the complexity of the removing elements algorithms from a binary heap. So we can improve up to the logarithmic time complexity for the general case, for the general case. So now let's look how this would work. So the hack here is to use some other data structure, but so now let's look at how we remove nodes with improved complexity. So to do this, we need to make use of another data structure from the heap and data and others that we use here, for example, array, we need another one that is known as hash table. So that is a data structure that we haven't covered yet, but I'm going to talk about it, I think, very soon. I think the talk next to the next talk, because next time I'm going to talk a bit more about removing elements. And now the central issue that the nodes are scattered across our heap, so they're at some particular positions, and so we need to scan them to find where they're positioned or indexed. We have to find their index. Instead, we would like to do a lookup to figure that way. So the way we're going to do, the thing we're going to do to improve to enhance the time complexity is that every node is going to be mapped to the index it is found at. So when we want to remove a particular node, we look up with what index it is instead of doing linear scan. So we already know at which position each node at, and we are just going to swap elements with their positions, with their indices. So I'm going to talk about it next time. So now we know how the a bit inefficient algorithm works, and we also know some hack how to improve the complexity using some unknown unknown hash table data structure. So I'll wrap up here. Thank you.
I have a question for you.
Okay.
Okay, so in polling, when you poll a binary heap, aren't you always removing the node with the lowest priority?
Oh, so
lowest value? Aren't you always doing that, or because in your examples, you removed elements that had higher priorities than the lowest node. I mean, I saw your technique, and it makes sense. But I thought, like, when you poll, isn't your interest to remove the node with the lowest priority? It's a question. I don't know.
okay.
I don't know the answer myself, but it seems like that's what you were doing.
Okay, so if I understand you properly, when we're polling, we are removing the element of the root node. So we are removing the element with the highest priority. So that is either the max value at the max priority heap at the max heap, or the minimum, the lowest value at the heap. So if we're processing the min heap, So in the example, there was the min heap because so the heap invariant was here that the parent node is always less than the child node. So here we had the min heap, and so in the min heap, the element with the highest priority is basically the lowest value. So here we are removing the element with the highest priority. So in others priorities, we're going to remove other values, lowest values or highest values. Okay.
The lowest priority, though. Okay, in a min heap, if if I understand you correctly, this is, I don't remember all of this, but the if I understand correctly, the in a min heap, the lowest priority is always the root node. Is that correct or no?
Oh, so yes, the
In a complete min heap, that is. Okay. So
oh yeah yeah
so in other words, yeah. So you're always removing the root node when you do your remove operation. You're always removing that root node, correct?
yeah. So we and the min heap we are removing the I think the element the node with the I think I'll so yeah in the priority queues yeah in the priority in the min priority queues or min heaps we are the root node is the node with the lowest value, but I think we can refer to it as the root with the highest priority, as here yeah, because the root node in the priority queues is always the node with the highest priority, but here the priority is to the lowest values. So if as it is lower, I think it would be it would had the greatest priority. I think here. So we're removing the in the min heap when we're removing the smallest values, we are removing the values with the highest priority. I think it works like that.
Sure. Yeah. Yeah. Okay.
Okay.
All right. I did understand. Okay. I just want to make sure I understood the theory. Thank you.
Oh, thank you. Well, I think.
Good talk. Good talk.
Well, I think Robert that you noted that from the I think the university or something like that. You have just to remember this to how can we say
It's
not
been
to
many years, but yes, I do remember something.
yeah yeah
But it's also, by the way, this priority queues are used quite a bit in computer science. So this is a good study.
yeah. These priority queues, I think they are, yeah, I think they're pretty useful as you are also saying.